Hi, my name is Manish Gupta, and in this video, I'm going to talk about this interesting concept called as gated attention for large language models. This paper won the NeurIPS 2025 Best Paper Award. Right, so let's get started. What is gated attention for large language models? Okay, so large language models basically depend on the transformer architecture, and in this transformer architecture, basically for every position, for every token, you basically create these QKVs, query keys and values. And the way you do that is using these three-weight matrices, WQ, WK, and WV. You use them to compute the scale dot product attention, which is basically, you do QK transpose, scale it with, square root of, divide by square root of dimension, key dimension, right? And then take a softmax and then multiply by the value vectors. And that's basically your dot product attention, right? If you're doing multi-head self-attention, you basically, concatenate all of those multiple outputs from those multiple heads, and then you apply a dense layer, and that's your output. Okay. Now, in the gated attention part, this is a very, very simple tweak. What you do is to basically introduce gates at various places. So you could basically introduce gate here, gate one, or you could introduce gates basically even after the QKVs, or you could also introduce a gate after the final dense layer, right? So, a gate is represented using this kind of a formulation. So the idea is that wherever you want to introduce the gate, let's say if I'm introducing a gate G1 here, what I want to do is to really modify the output after concatenation, right? So my Y is basically going to be the output after concatenation. Okay. So basically after gating, Y will become Y dash in that sense. So after the gate, it will be called Y dash, right? So the gating is actually done using this simple dense layer. What it does is to take some input X, where basically the input X could be really here. So they are the hidden states after pre-normalization. So, after the pre-normalization is done, you take the hidden states and that's your X. And then you have these gate parameters W theta. You apply a sigmoid on top of them so as to basically decide the gating values, the gate values themselves, right? And basically what you do is to really multiply these gate parameters with y so as to decide how much your y should be attenuated in that senses. Since you're using a sigmoid function here, your gate values are going to be between 0 and 1, so your y is going to be reduced in some ways. Some of them will just become zeros if this gate value returns 0, right? So that's that. Now, they try out in this paper, they try out various settings where how gates can be applied. So essentially gated attention can be done in that senses. So first they vary the position. So basically they try out gates at various places. As you can see them here, 5 different places. They also try out different granularity of the gates. So the gates can be applied like head-wise or element-wise. So you could basically say that, hey, for the entire head, I'm going to use the same values, or you could basically apply, a different value of the gate for every position separately. So that's what they do. Third, they also do head specific or head shared kind of gating, which basically means that for different heads, you use different gate values, or for every position, obviously, or you basically just share those values by taking an average, across various heads for each position in that senses. Okay. Gates could be applied in a multiplicative or additive manner. So essentially this particular operation here, this could basically multiply to your y or add, right? So they could be done in a multiplicative or additive manner. Finally, the activation function that you use could be, either, it could basically be, different activation functions. So you could use a CELU activation function, or you could use sigmoid activation function, whatever activation function here, right? Here it is shown as sigmoid in that sense. Okay. So what did they find? They found that doing gating for these large language models, for the attention part of the large language models, is very helpful. In fact, they found that this gate G1, this particular position, is the most effective. It leads to the maximum, to highest minimization of perplexity. Remember, perplexity lower the better. So basically, it reduces perplexity significantly compared to other positions. Now, the second position that is best is this gate G2, which is applied to the output of the value layer, right? So other positions do not really cause significant reduction in perplexity, but the position after concatenation of these multi-head attention values, and also after the value computation, basically both of them are good places to apply the gates. Correspondingly, there is also significant improvements that one can see in the accuracy values for the MMLU benchmark, right? So gating literally helps. It actually gives you better performance from these large language models. Not just that, gating also helps in terms of stable training. So you see this particular chart on the right side shows you training. So x-axis is steps, total 360k steps that have been used for training. And with a learning rate of, I think with a learning rate of e raised to 10 raised to minus 4, but we'll see more of that later. And as you can see, the loss basically, the gray curve here is the baseline without gating. And basically this light blue curve is basically with gating. So you can see that with gating, the spikes are much lower, which basically means it leads to much stable training and also lower loss in that senses. So gating helps in that senses, right? Now, how does gate attention perform in more detail, for mixture of expert models? So they performed experiments with 15 billion parameter mixture of expert models with like 128 experts, of which 8 experts are active for any token, which basically means that at any point of time, 2.54 billion parameters are active. They trained these models on 400 billion tokens, which are subsets of a larger 3.5 trillion high-quality token dataset. They trained for 4096 max sequence length. And they used GQA, so grouped query attention, which basically means that multiple groups of attention heads share the same key and the values. Okay. So there are many results here, and they try to experiment with various settings. So, changing the gating positions, changing the gating granularity, head specific or head shared, and so on, as I discussed on the previous slide, right? So the baseline here is basically the baseline mixture of experts model, which basically uses, I think, it sort of uses Q heads, which is basically, which is basically, I think, 32. Yeah, I think it basically uses 32 different query heads, and it uses 4 as the number as the keys, right? So there are 4 different key heads. So the group basically is defined as basically k equal to 4. So, right here it's written. So baseline uses q equal to 32 and k equal to 4. And all methods basically use the key dimension as 128. But what they also try to do is to make the baseline better by adding some more parameters. So they basically tried with k equal to 8. So 8 different key heads and then 48 different query heads, right? So both of them increase the number of parameters by 50 million or 200 million, as you can see here. They also tried increasing the number of experts from 128 to 4, and they make all of those basically activated. So which basically means that that adds a huge number of parameters, like 400 million parameters to the model. Okay. Now, when you do gating, what do you observe? So when you do gating, obviously you can do gating at different positions, and these are all element-wise gatings, which basically means that there will be as many gating output values as the sequence length, which is denoted by n here. Number of query heads, because G1 is basically being applied, you see right there. So number of query heads, and essentially also decay the dimension of the keys, right? So that's that. And so on. So basically, depending on where you apply it, the size of these gating parameter or the gate weights or gate values is going to be different, right? So, however, if you notice, although this element-wise G1 gate has like quite some parameters, 201 million parameters, the value head basically has just 25 million parameters. Now, of course, if you basically just do, so this is basically all element-wise gating, right? If you basically, and the good part is that this one gives you the best results. So the right part of the slide actually talks about the results. Average perplexity, the lower the better. And then it also talks about the performance on 4 different benchmarks like HELA-SWAG, MMLU, GSM-8K, and CEVAL, right? So as you can observe, you see the minimum perplexity is actually with the scaled dot product attention with element-wise gating G1, right? So essentially when you do gating right there, G1 after the concatenation of the multiple head outputs, right? So however, it does incur a 200 million parameter cost, right? It also basically leads to the best results on MMLU and GSM-8K and reasonable results on HELA-SWAG as well, right? Now, if you think about the head-specific or head-wise gating, right? Head-wise gating rather than element-wise gating, well, the number of extra parameters are much lesser. I mean, it does improve with respect to the baseline results. Now, obviously, these results are not as good as the element-wise results. Element-wise is best. However, even head-wise gating actually leads to significant improvements in the model performance in the model performance with very small amount of extra parameters built in. Okay. Now, I mean, if you think about it, gating is basically very quick to perform, and therefore the latency basically introduced by gating is less than 2%. So that basically is not a concern in that sense. Um, Now, from a head specific versus head sharing perspective, yes, I mean, head sharing is actually a bad idea because it leads to higher perplexity and not so good benchmark results. So that's that. So head shared is actually worse than headwise. Also, multiplicative gating is actually better than additive gating. And sigmoid based gating is actually better than SILU, some other activation function based gating. Okay. Now, how does gated attention perform for dense models? So we talked about mixture of expert models on the previous slide. How does it work for dense models? So they experimented with like 1.7 billion parameter dense models. And they did several experiments in terms of varying the learning rate, varying the number of layers, and varying the number of tokens on which the pre-training is performed, and so on. Okay. So in this particular case, they did not increase the number of parameters at all. So if the number of parameters increase because more parameters have to be added because of gated attention, well, they reduce the feed-forward network width to maintain the same parameter size. Okay, so the number of parameters in all the models are exactly the same in all the variants that you see here on the slide. Okay. And what you observe is that whether, I mean, across all of these settings, basically getting helps. Okay. So essentially, there is a baseline and there is this SDPA element-wise. So this is element-wise gating. And as you can observe, perplexity reduced and benchmark scores actually improved. Okay. Similarly, if you observe here, where the training is actually done, pre-training is done for much more number of tokens, you do observe that the baseline, yes, baseline also improves, but then the gated attention-based LLM actually comes up with even better performance, right? Um, and the interesting part also is that you could try to make training more stable with slightly higher learning rate using other kinds of methods like the sandwich norm method, where you could do normalization between the attention and the residual addition rather than doing it after the residual addition, right? But even there, the perplexity reduction is not as good as the perplexity reduction that one can obtain using this element-wise gated attention. Okay. So basically saying, yes, there are other methods to actually improve the performance, but well, they don't perform as good as the gated attention one anyway. And they're orthogonal. So maybe you could do both and then see how which one works better in that sense. Okay. Or how does the combination actually lead to better results? Now, the other interesting part is that they also experimented with expanding the number of layers, expanding the depth from 28 layers to 48 layers, and the performance benefits actually continue to happen. Finally, as you can observe here, 48-layer deep model with 1.7 parameters and like large batch size and large number of tokens. If you look at the baseline with a learning rate of 8, it actually starts diverging. However, with SDPA element-wise gated attention, it doesn't diverge. It, in fact, leads to higher performance, and lower perplexity. So basically, it means that getting improves performance, it improves stability, and therefore, leads to better scaling. So you can actually use larger batch size, larger learning rate, and the training does not diverge. Right? So why gated attention works? I mean, you must be wondering, this is great. This is a very simple idea. Why does it work? So there are two possible reasons that the authors provide. One is gated attention introduces non-linearity. So remember, this first equation is the way the standard scaled dot product attention works. So you basically have this dot product QK transpose that comes in here, and then you multiply it with the value matrix and with the value matrix, right? And the value matrix is basically obtained by looking at the jth token in the input and multiplying with the value weight matrix, right? So you basically add up across all of those heads, and then finally you multiply with the final output matrix. So that's what you do. And the interesting part is that since there is no nonlinearity between, this value head and the final WO that is applied, you could basically literally merge these WV and WO into a single low rank matrix. So you could basically literally do this. This is equivalent to the expression on the right side, which basically means that there's no nonlinearity here. You could basically merge this into a low rank matrix. So what they have done is to basically bring in gating, right? So the G2 gating works like that. It applies after the value matrix. G1 position gating actually works like that. It basically brings in nonlinearity before the WO matrix is multiplied. And bringing in this nonlinearity is what basically makes gated attention work better. Okay. The second reason is that gated attention also introduces input-dependent sparsity. So remember, in a previous video, I talked about attention sinks. Attention sink is this phenomena where large language models basically pay a lot of attention on the first few tokens, specifically really on the first token itself. Okay, so on the right side, what you see here at the top is the first token attention score. So across layers, right? So in the first few layers, well, there's no attention sink problem. But as you see, as you go higher on the higher layers, you observe that the first token actually gets a lot of attention. Mean attention that the first token gets is like 46% attention across all positions in the input. Okay. Um, However, when you do a gated attention on the lower plot, as you can observe that the first token actually gets a mean attention of just 4.8%. So 46 becomes 4.8%. Thereby, the attention sink problem gets mitigated. Okay. The idea is this, that this gating is really input dependent. So as you basically have noticed, the attention gating basically makes use of the input. So the gating is actually input dependent and head specific as well. That leads to sparsity. So when you do gating, obviously it's a number between 0 to 1 for every value, and therefore it leads to sparsity. And that reduces the massive activations. Since it reduces the massive activations, it leads to basically both mitigation of attention sink problem, and also it improves the training stability, and and therefore you could actually train with larger learning rates and larger batch sizes in that senses. Okay. So this is also observed in the table here. So essentially in this table, there is baseline and there is this attention getting element-wise and attention getting head-wise, both of them using activation function as a sigmoid activation function. And as you can observe, the gate scores are actually, this is the average across all the gate values. So you see they are very, very small gate values. And then this is basically the activation. So the activations that are generated basically, what is the average activation magnitude? So magnitude of the activations is super high for baselines, but it's so low. In fact, it's basically almost like 10x, less than 10x, right? Which basically makes the training more stable. This one basically shows the attention which is paid to the first token across all layers. And as was also observed here, the attention with the baseline is like 46.7% attention, while with these scale dot product attention with gated attention kind of method, it's basically very small, just like 4.8% with the element wise gating. Right, which basically helps mitigate the attention sink problem. So in summary, this is a very, very simple idea in this paper. This paper explores the role of gating in the standard softmax attention, which is like the crux of the transformers and the large language models today. This attention gating in the attention computation, actually it impacts and makes performance better. It helps better stability while training, and leads to scalable training in that senses. So they tried different settings for this gated attention, and they find that head-specific multiplicative gating with sigmoid gate after the scale dot product attention is the best. It enhances non-linearity, it introduces input-dependent sparsity, and it also helps mitigate the attention sink problem. So that's it for this video. Hope you enjoyed the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage.